There is a slight change in the program in the sense that David Newberry was supposed to chair the session, and because he didn't attend the presentation, so he asked me to chair the session. My name is Janusz Bialek. I'm from Durham University. My background is power engineering, but I dabbed into economics a little bit. I think, well, the second, probably the reason I was asked to chair the session is just to shut me up, so I don't say too much and dominate the discussion. Sounds like a clever plot. So I think it was extremely interesting and thought-provoking presentation by Sean this morning, and we've had some attempts at discussion before the break. But I think now is the proper time to discuss the whole situation. So I think we should start from Sean's presentation in the sense. Do real-time markets matter? Is it complete fallacy? As he said, do we need additional markets or maybe we don't need markets, maybe we should just provide control signals. This is the point which Frank has made, that maybe we should just mandate, we should use control as it is, Lagrangian multipliers control systems rather than as a price systems, as a shadow prices, because that would incentivize people to do funny things, tricks and gaming and etc. So open the floor for discussion, please. Okay, Chris?
Just a quick comment that many systems who have location marginal price market regulate bids to marginal costs. So to an extent, is that what?
That's what Chile does, yeah.
See?
That's what Chile does. Yeah.
Ireland does this as well.
Yeah.
In Ireland, they audited, I think, marginal cost, if I'm correct. Is that true, David? No.
Actually, can I, just because David, you weren't in my talk, I just want to clarify that I didn't really say that. So the analog, I made an analogy with an airplane. So where has economics been really important to the airline industry? There's been incredible innovation, for new engines and actuators and control systems. And they've put out auctions for products. They say they need a jet engine with so much thrust and so much weight, and because of the competition to make money, selling these products to Boeing, there's been fantastic innovation. So on a long time scale, economics has a tremendous value. And it's just I was joking that on the flaps of the wing, we're not going to have consumers putting in coins to make the flaps go up or down. And so it's the time scale differentiation I was making. There's a point where real-time control is there. And I quoted Coase, because Coase in his work says, why do we have a dictatorship? A firm is a dictatorship. Why would we have that in a free world? There's basically a dictator who's the owner of this company who tells the people what to do. And that differentiation is because of transaction costs. And that's very analogous to the ramping costs in the So that separation of spatial and time scale is recognized in economics. So I'm not at war at all with economics.
So would you go for market-based solutions or mandated solutions?
No, markets, but exactly how Boeing does it.
Sorry?
Exactly how Boeing does it. I would. So I know it's not trivial. I'm not an economist, but I know what MISO did. Midwest ISO had this incentive for responsive services, and they would give a payment each day based on services delivered, and that included the wear and tear.
So that was post-fact, basically.
Yeah,
at the end of the day, calculated
you basically have people engaged, and you look at the reliability and quality of service provided each day, and you give them a payment each day based on that, and that's not trivial. I'm not saying that I've solved the problem, but that's the form of the solution that would work. And MISO proved it worked last year. They got 20% or 15% increase in responsive generation just by a very crude incentive, and that's a crude economic instrument that works.
Any other points? And then Yves.
Well, here's a question based on not having heard your talk, but it's relevant to the question of how you secure the various services that you need to balance and deliver reliable electricity. And it's a question of, do you, in a capacity payment system, specify precisely what it is you want and then have the auction to determine that? Or, and this sounds like the MISO solution, do you say what it's worth and you then provide incentives to people to provide it on a minute-by-minute basis, by the sound of it, or ex post reconciliation of what they've done? So are we just confusing the difference between, say, the Irish market, which is an ex post market, and you find out after 4 days how much you actually are going to get paid, or an ex ante market in which you put bids and offers into the balancing mechanism, and that then determines who gets called?
Yes, well, the trouble is, I'm not prepared to, like, just like if you told me how would I control the grid, I'd say, I don't know. If you told me exactly what precise way I would design an auction system, as Boeing has successfully done, I'm not going to say, I'm not an expert in that. But I know the form of what has worked in the past is to say, I need this bandwidth of service, I need it reliably. And I don't know up front if you're going to be reliable. And so it has to be after the fact. I'm going to look at the service you gave me over the day or the week, and I'll pay you based on the contract you've just signed. And it would be a two-part contract because there are risk issues you'd have to mitigate. And it's not, there's no way I'd say solved it. I know the form of solution that most economists would accept, and that would, and is provably would incentivize the right long-term infrastructure. Long-term, like ancillary services 10 years from now, would be developed through contract mechanisms like that. There's empirical evidence to show that.
Okay, if you want to.
I was amazed by, I already expressed that, I was amazed by the statement that the real-time market, real-time prices are irrelevant. So there's been a lot of literature explaining that it should be the basis of the whole pricing system. And the argument was very simple. It's in real time that you can check which of the constraints of the systems are tight, and hence that you can get evaluation for relaxing that tightness, and so that is useful both for the short-run management and for the investment. And in fact, the argument was made, I guess, in a very clear way a long time ago by Bob Woodson, saying that the problem, and that's where the debate comes, the problem is that getting the right price in real time is so complicated in terms of optimization, and in terms of the time scales on which the market has to clear, that you cannot clear so many markets that are interconnected in a short period of time, and hence you have to resort to optimization to do it. But then the thing is that the reason for that was that you had many markets, that there were a lot of interactions, and hence that the prices that you would get in real time were for different services. They were for location, they were for the time, obviously. They were for the ancillary services, even though in those days that was not very much explained. Okay. Now the real problem is that in the very beginning of the restructuring, when I said engineers who were quite happy in the very beginning to just show the merit order and to discuss in terms of energy, and the economists who were quite happy to design a market on the sole basis of energy. And so the real-time price and the price itself has in fact been drastically simplified, which is what you said. And on top of what you said, one could also say that in the price, there should be the price of scarcity when the resources are tight, and that was not in Schwepp's argument. And in fact, where one finds the problem that it's difficult to distinguish robbery for efficiency, because as soon as the price goes above marginal cost, whatever it means, to reflect scarcity, people like David would say that's an abuse of market power, and so they would claim robbery.
But they couldn't figure it out in New Zealand.
And so there is a
$25 million. There's no way of knowing. But the same in Texas. They
I
don't
think
know
that
the
just
motivation.
stating in the beginning
Yeah.
that the basis of the restructuring in the US is just wrong.
No, I didn't say that.
Well, but the
No,
real-time
so
prices.
You're saying that.
No, the real-time price has no value. You said that.
The real-time prices have no value. I can
Then you're
give
right.
empirical evidence and scientific, economic evidence of
But
what they do.
how can you say that they have no value? Well, what?
That's a competitive equilibrium analysis. So first, so two results.
Well, they
I'm talking
define the
about
tightness
physical
of all
problem.
the constraints of the system.
No, hold on. I'm talking about the physical problem. So first of all, the new gas generator in Florida is going to be $1 billion, and it's going to take several years to build. The entire cost is sunk cost. They'll make a few billion, but it's all it's all sunk cost. Number one, and so this could be the second. Okay, that's number one. Number two is that if you actually take a competitive equilibrium model, and you instead of looking at snapshot markets, you actually look at what people would really do. They would take into account the fact that they have to solve an optimization period of a long time, and it takes time to ramp up and time to ramp down. When you solve that, and it costs them money. The faster they ramp, the more expensive it is. In a competitive equilibrium model, you find the average price is the average marginal cost, so the sunk cost is lost. $1 billion, hold on.
But that's not true.
No, this is a competitive equilibrium model. This is in the way it's done today, the way it's done today. And hold on, the cost of wear and tear is not there.
If you work with a complex model in a dynamic setup, the ramping cost or the limitation on ramping will be in the marginal cost in real time.
Well, it depends on how you design.
But the problem
it depends on what you put in your economic model.
Well, the thing is then, no, the real problem there is that what the theory says is that you should put in the marginal cost whatever contribute to the marginal cost. The problem starts when people will say, and traders in particular, would say, well, that's too complicated.
But you're missing.
So we simplify, and then you have the problem of missing market, of the incomplete market. You have a lot of things that should be in the market which are not there.
This is a complete market. I should be careful.
It's a complete market.
No.
The ramping rate is in the cost.
Right, of course.
And then
it is a price-taking model. It's not a complete market. It's a price-taking model.
Okay, well, but then you can be price-taking on just energy, or you can be price-taking on something which is much more complex than energy. The problem is that the marginal cost should reflect whatever contributes to the marginal cost.
Just can I interrupt? Stan wanted to make a point.
I get the impression, listening to all of this discussion, that a lot of it comes back to Frank's point about the difference between Lagrange multipliers, which everybody accepts are valuable at all times and probably on all time scales of the model, unless the model is too simple for the time scale. Which are valuable the whole time. Obviously, you want to tell people when not to generate because it's because it's much cheaper to do it at another time and so forth, and bringing and competition where you have people who are gaming the system. So the competitive, so shadow prices. And I get the impression, summarizing what Sean said, which is a stupid thing for me to try and do. But Lagrange multiplier is good, shadow price is bad.
That would be going back because engineers use Lagrangian multipliers for ages to solve optimal power flow, which is to solve congestion. Yes. The difference is that the shadow prices, they did this economic interpretation of Lagrange multipliers are shadow prices, which is competition. So are you saying that we should go back to CGB running the power system in this country and using happily Lagrangian multipliers to control output of power stations, but it's bad if you use them for pricing purposes?
It's time scales, is it not?
Because question as economists here, because presumably if you think of this, if you think, so think of a large-scale optimization model that you think is a reasonable representation of the physical reality of the generating constraints and this, that, and the other, then that will give Lagrange multipliers at whatever level of detail you're prepared to model. Now, when those get, and those would describe a decentralized control system where actors in that decentralized control system act as price takers to those Lagrange multipliers. So far, so good. But then the next point is, suppose that you make those Lagrange multipliers actual prices for actors that have a strategic capability to not just act as price takers, but to decide what they want to do. Then presumably the economist's intuition there is that it depends on what market power they have. And that market power might be local in space or time. It might be, whatever it is that causes strategic behavior to give you a lot of gain over price taking. And presumably there's quite a lot of intuition or knowledge from economists about when that happens.
Yes, and I think the resolution we've reached is that the engineering solution of the Lagrange multipliers was brilliant if everybody did what they were supposed to do, but it was crap when it came to incentivizing the particular people in the particular power stations to actually do it. whereas market prices which affect their pay packet have a rather more powerful effect on whether they actually polish the turbine blades properly every week. So we come back to the question of how do you get the balance right between solving a very complex optimization problem and providing all of these incredibly large number of participants in the activity with the right incentives to do it. And I think the compromise solution is that for some things like energy, a price is actually quite good, and you can use that and trade it, and markets work reasonably well. But for a whole range of other essentially balancing and ancillary services, which are changing second by second, it's not going to work. So effectively what you do is you have a trade-off between, do you use these Lagrange multipliers which give instantaneous market power to people who hire the smartest Cambridge mathematicians to figure out how to make a bomb, or do you design a contract for a range of services, and a contract removes the incentive to exercise market power, because essentially you're only being rewarded by the deviations from the contract, and if those are small, then the incentive to engage in those deviations is fairly small. So
How do you value those contracts?
So it comes back to how well can we search for the set of contracts that are needed to elicit the supply of the right kind of ancillary services and to provide the incentives for people who may not realize they have the capability of offering them, particularly on the demand side, to offer those. And the worry is that civil servants get to design these contract mechanisms and do it entirely incorrectly. And National Grid and the system operator, who have the expertise to do it, have no incentive to do it because they're not managing the system or collecting any of the money. So we do have a really interesting mechanism design problem of how do we make sure that the right kinds of contracts for eliciting these services are provided and then the people respond to them. And that's a non-trivial problem.
You've really let me down, because I was expecting a big debate. but one thing, there was one example I gave that showed a bureaucrat come up with a ridiculous proposal for exactly what you said, contract. With Midwest ISO, they came up with a incentive for responsive generation that I don't know what it was based on. It's definitely not based on engineering. It was just some crude estimate of wear and tear on generators. But it worked in the sense that, it's only a small, the ancillary service part is not a small amount of energy. It's between 3 and 10%. Even though it might not have been efficient, it wasn't based on any complicated economic grounds. Just by having this crude contract in place, they got a huge increase in incentivized ancillary service generation, amazingly in 1 year. So the bureaucrats, sort of got it right, and something like that could be then refined now. So it's a starting point. But it's exciting to hear you say that. I couldn't agree more.
What was the alternative before the contracts?
Well,
How would you communicate it?
So I would let me give an example. I know, of course, I'll be shot dead because I don't know. I know for certain that I couldn't design a highway. I wouldn't know how many lanes to put in and what timing for speed lights, and I wouldn't pretend to be able to design a control system for an airplane. And I'm sure not going to pretend I can do contract design. I don't know mechanism design. But I can tell you I told you the formula solution I could see is that I wouldn't want MISO to tell me what my cost of providing services. So ancillary service, I want the people producing it to figure out what it costs. So you would want contracts for services for I want this much bandwidth of regulation service, that much capacity, and so forth. And what would happen? So at first you'd have the gas turbine generators offering bids. It would be very hot. But eventually Ivana and I would come with our HVAC systems, and it would be a penny, because we provide the same service by ramping up and down HVAC systems. And you see the incentive. I have no incentive right now to quit my job as a professor and open a business selling ancillary service in Shetland Islands or in the Pacific Northwest. But if I could bid into a contract to provide these services, I'd be up and running, just like the telecommunications industry was a decade ago.
But how do you value that contract, those contracts?
I can.
That's-
Oh, well, they would be. they'd
to
be
value the
fair.
contracts, you need some prices, you need a market mechanism.
That's what the auction does.
Yeah.
I mean, you say what you want, and then the market tells you what it's going to cost you, and then you think very carefully whether your security of supply standards are what they should be.
And what are the characteristics of those contracts? So do you have a, so for instance, if it's just for capacity market, would you just have a capacity? Would you have some duration of utilization of that capacity, or something more? And do you have some ramping possibility in those things? Those contracts can become extremely complicated depending on the service, the description of the services. And
Oh, Frank.
So this seems to be a really interesting discussion. But sometimes there might be such a market mismatch. It may be that there's something that's very cheap to provide, very easy to provide, but just no incentive to provide it.
Today.
Now, in such a circumstance, it might be that some very crude intervention of a regulatory form might make sense. So let me give an example, which my information here is a year or two out of date, so it may have changed. Other people may know more recently. But Dynamic Demand was this consortium that put together this idea of a chip that you put in a fridge. And the fridge, a hysteresis loop, it goes on or off according to the temperature in the fridge. The chip changes it so that it looks at the frequency of the grid, which is easy for it to measure. And so it's a two-dimensional hysteresis loop. It looks at both the frequency of the grid, which tells you the instantaneous mismatch between supply and demand in that synchronized region. It looked at the temperature of the fridge and this, and that changed, so it came on, so basically it was sympathetic to the grid in the sense that it came on a bit early or it went off a bit early, if that helped the grid. And their estimates of the value to National Grid in terms of reducing needs for other ancillary services was a net present value of about $30 a chip. And at the time, that chip cost $5 to produce, and probably costs 5 cents now, because that technology, one knows its price path. Now there's an example where there's zero incentive on fridge manufacturers to include it in the fridge. There's zero incentive on users to buy fridges with this. There's zero incentive on everyone in the system to do anything, which is really very cheap to do. So that kind of looks like something where you say, well, it seems to me you have conditions on electrical equipment. If it plugs in, it has to satisfy certain range constraints on voltage, inductance, this, that, and the other. One could imagine very simple slight change of that regulation that says that systems that are on or off, that turn on and turn off, which is quite a large amount of air conditioning, water heating, and whatever, a condition of those systems. They have conditions on the transient now when they turn on and off. And yet the technology is such that that kind of crude condition on a transient is probably harder to measure and enforce than is these sophisticated measurements of frequency, simply because the chip design to get to frequency has got cheaper and cheaper and cheaper. So one possibility is to just say, look, we can see we want to regulate this. There's so much value to be got here. It's very difficult to construct a contract. How would you construct a contract to provide this incentive? It would be extremely difficult to construct a contract. You'd be designing a very complicated contract whose outcome you knew. You knew what you wanted the answer to be. So one possibility there, I can see the lack of sympathy for mandated solutions and for regulation. But sometimes if the answer is one that's relatively straightforward and simple, and where there's a big economic incentive to the system to do it, but no real way of seeing how to make a decentralized price-based incentive, then maybe a small bit of regulation.
But would exactly, Andrew, would National Grid be happy with that kind of solution? Let it go.
I don't know. I can't answer that question. What I can say is that could you not have a competition and auction for regulations? Because what I'm thinking is, suppose you as a regulator thought, what a great idea these fridges are. Let's put in a regulation. And then Sean comes along with a slightly different scheme that doesn't fit into the regulation framework, which in fact is cheaper, would be a better thing. Sean wants to make money out of this, but the regulations don't allow him to. But if he could say, well, actually, we've got our lawyers to come up with this regulation, it'll cost less, you could have a kind of auction
Yeah.
for the regulation.
It depends how much is to be won there, because you know the old numbers were $30 net present value, $5 cost, and if the new numbers are 30, I mean, because basically, do we worry too much about the constraint on the voltage on the transient when the fridges come on? Not really. It's probably not the right constraint. It's probably a better regulatory constraint would be better now. But the amount of money we're talking about is very small because it's all very easy to do. So I guess it's just a matter that there might be a better way to do it. But where is the big win? The big win between $30 and 5 cents, one can see. You know, you might get other wins between 5 cents and 0, but you've got most of the benefit.
And nobody's saying it's the whole solution. So this will be 30% of the regulation reserves, you know, and then there'll be something else from the pool pumps and something else from gas turbine generation. So there'll be some uncertainty introduced here because the decentralized controls of those buildings are not going to be exactly what you want. And so you're going to introduce, you know, you're going to have quite a bit of residual uncertainty that you'll have to.
Well, so the problem for the grid that it'll produce, as you can see, because you'll have uncertainty over 5 years about how much.
Yeah,
Much,
just,
but
you
the
always
uncertainty
have
for the grid is what Jean-Yves spoke about. What will happen is that the demand will be displaced in time by 3 or 4 or 5 minutes because the fridges and everything comes on more slowly. So it'll be this problem that there's sort of an incipient demand out there that's been postponed by a few minutes that you don't quite know how much is going to come back and hit you because these fridges will turn on.
This is Jean-Yves' frustrated demand.
That's right.
And his,
that's right.
And his
So I can
model
see
shows-
National Grid having an issue that they may think, well, we're worried about that.
But that's a control problem that I think is easy. I think
Yeah,
you can solve that.
I think it's easy, but I think it's doable.
But you're concerned about the risk problem. It's the same thing I am. Is that you've invested money in buildings to get this ancillary service, and then suddenly somebody finds out they can build a 100 megawatt battery for nothing. And you can drill to the center of the earth and use the center of the earth as ancillary service. You're worried about that long-term risk issue, and we always face that. We had to stick in TCP/IP. If we'd waited for the optimal solution, we would have waited forever, and it's not perfect, but it works well enough, And so this won't be perfect, and it won't be, we're not expecting it to provide all of our needs. It's just going to be one layer.
So, this is an example of where that interface between the economics and the engineering, right? So you've got this sort of this mental model that if you had all of the branch multipliers at the precise level of detail, then if only you could make. So the question is, where do you want to make those very sophisticated real-time prices the thing that drives the market? Presumably not all of them, because they'll have to have derivative terms in them. To make the market complete will be huge and will be a huge task, and will inevitably, because it'll produce all sorts of areas where there's market power, be manipulated. So somewhere you want to say, here's a thing where we want a real-time price with the energy for things really where it's quite hard to meet the demand, where it's quite hard to satisfy the transmission constraint, where it really costs money to do it. But then all of the things which actually don't cost a lot of money, if only they were done well, you don't need real-time prices to drive that part of it. So the interface between the economics and the engineering is trying to work out which are which. What is it that's easy to engineer if only you work out and control everything, and what is it that's hard to?
Well, the real practical problem is that the important decisions to make are investment decisions, whether it's in the bridge, whether it's where you put the power stations, whether you reinforce the grid more than you might otherwise need to. And that's a question of predicting what the consequences of being in one place or at one time or with one technology are rather than another. The real time is only useful in that if you could predict what it was and work out over a reasonable length of time what revenue you would get, you would then say, I will supply that service there. So the more challenging question is, can you do this better than we do at the moment, not perfectly, but better than we do at the moment, and can you formulate that into a set of contracts or price signals which give people the signals that make those investment decisions? And then running the system is a system operation thing.
Well, based on what you've said, of course you could. I mean, sure, absolutely. I mean, you already outlined what you think would work. Is formulating some sort of contract for the kind of services.
How would you price them?
Well, like I said it already. So
How would you structure them?
that's not. I don't think that. I'm surprised. I I think that's, isn't that easy? I mean,
Sure, to just try and pick up
I
the
don't
example. The
understand.
example you gave was the $1 billion sunk cost for something which, according to the equilibrium thing, would be the market would suggest, correct me if I got this wrong, that the person invested in the billion would take the net present value of the expected price out to the infinite future on the real-time market. Quite a lot of that income is lots of money that is collected over short periods of time. And I suppose Sean's point is that that's such a variable net present value that the risk-adjusted cost is much higher. But then the other point, of course, is that the risk is not just that it's stochastically fluctuating. It's that it produces numbers like 9,000 or 20,000 or whatever, which produce political intervention. And so
You
that...
solve both of those with contracts, because then you don't have to see the politically embarrassing things, and the certainty that the contract gives you reduces the financial risk.
So the form of contract would be a contract, what, government to power station?
Not necessarily.
Or-
It could be from the system operator to the supplier of the services.
well, it works. I mentioned in my talk, New Jersey has contracts with consumers, and there's a $50 upfront cost and a very small reduction in rate to get ancillary service from the customers. I mean, I don't think that's the right way to go. I think that's too much risk for the utility company. But it works now, and so these things can be improved with time. I mean,
You cannot have a long-term contract with a small consumer.
I don't think it makes sense.
You
either.
can have it
It's a
with
test
credit
study.
for the-
You can. It's
Well-
through the grid. In order to be connected, you have to pay every year a certain amount.
Yeah, but that will not assure you the long-term revenue.
All I meant is I prefer Frank's solution. I prefer that for these very simple things. There's a problem. I mean, there's a tragedy of the commons, is what it is. I mean, everyone wants reliability. Everyone wants a clean park, and nobody's going to clean up. But the fact that the value of an individual is so small, it would make much more sense to have standards for appliances. For those things. Contracts with consumers consumers can't evaluate them, and there's risk to the supplier.
So what happens? So the market has had long-term contracts, hasn't it? And so what has prevented that market growing larger or?
Abuse of dominant position. In fact, when they were the incumbents at market powers, they were asked by competition authorities to stop them. And in fact, we had something that gave a true incentive to build. But as long as that thing took place with a generator that was dominant on the market, then that was seen as abusive. And the problem is that you could not contract across transmission capacities because the transmission system operator would never guarantee the transmission to the capacity.
Right.
So in fact, you were bound to sign contract with dominant producers, and hence they were forbidden.
Right.
So if, on the other hand, if we had the financial transmission rights on the transmission capacities, then that would be possible. But as long as we don't have them, this is not
The
possible.
FTRs, Goldman Sachs makes it's $1 billion a year on gambling FTRs in the U.S. And,
Yeah, it's true that it's a market that doesn't work.
and Deutsche. Did you hear about last month? Deutsche Bank had to settle $250 million because they were sending in false price signals to move the simplex method and get the pivot points here instead of there, and so they settled out of court for $250 million. So these financial instruments are, there's a playground for financial companies.
No. Andrea?
Can I just interject here, because we've talked a lot about the economics, and there are non-economic problems here to solve as well. And that may be absolutely obvious, but I think it's worth saying that I said I wouldn't answer Janusz's question about would the grid be happy, but I'll sort of allude to it. If you've got a system that is autonomously behaving and controlling and regulating, there are times when it's going to go wrong. It's not clear to me when you talked about Florida being able to cope with half of the fluctuations in the US, if you're talking about what would happen if, 5% of your generation just suddenly went offline.
No, that's not what
So
I mean.
you still need services there to cope with frequency fluctuations, which are down to unexpected events. If I were sitting in the control room now listening to this discussion, I would want to know that first of all, the types of services you're proposing aren't going to clash and have a battle with the types of services that are there to control the frequency when we have very big deviations. And they're not going to clash with the time when to use your analogy, the pilot just looks at the ailerons and says, the automatic things aren't working, I'm taking over control. And I would want really good guarantees that if I needed to take back control of the system to recover it, that the services that were being provided weren't battling against me.
I think it's an important point. Yeah. Now, Chris.
Yeah, another, well, actually much broader question of process on market design, which is how do we actually determine whether a given redesign of the market is a good idea, or which of different options is a good idea? Because the way that this is typically done in this, and I mean, across a lot of government policy now, is so-called impact assessments, which in practice means usually a large-scale mathematical modelling study, and there's always very considerable uncertainty in how these models represent the real world, and therefore there is very considerable uncertainty in within this process as to which option for market design actually is best according to the metrics set. So there's a questions for people who've already participated in this discussion. Do you think that this is a sensible way to proceed, or what do you think the appropriate way of making these decisions on what constitutes the appropriate market structure is?
Is that directed at me?
Well,
Yes. Well, the first and obvious point to make is that electricity obeys the same laws of physics everywhere. And there are a very large number of models out there in the world, and some of them work better than others. And the first point you make to any government, ministry or regulator is, have you gone around to find out what else is working and compared it with what we're doing here? Whereas what we usually do is go out to consultation, and the people who show up at consultation meetings are the people whose money is on the line, and we want to make sure that the outcome is beneficial to their bottom line rather than necessarily system optimal. So that's the first obvious thing. And the second obvious thing is, well, 2 points. One is we need to quantify to see how well we're doing, and that means massive more transparency of data. I mean, comparable to what the US puts online. If I want to know what the forced outage rate of a particular kind of gas turbine is, I don't go to National Grid, I go to the American database. So it's transparency and allowing people in this room to analyse and see how well are we doing against alternative models. And secondly, we have to recognise that systems evolve. I don't know how many code reviews or changes there have been in the balancing mechanism. It must be in the hundreds. And so we have to put in place a governance system and a system of evaluation that does that sensibly, because we're never going to get it right first time, but we might be able to incrementally edge towards something that's better.
Maybe widening a little bit of discussion. This is dominated by this group of people, so in the audience, any questions, please? To widen discussion before we continue on this one. I don't see much appetite for answers, for questions. Okay, so let's go back to Frank.
Okay, I can say that there's lots of other things we could discuss, but there's something I wouldn't mind just pursuing a bit further to pick up the point that David mentioned earlier. Imagine the big problem of trying to incentivize investment. And so long-term contracts look like, why isn't that a way to do it? You match the long-term requirer of electricity, which is a distribution network or an aluminium smelter or whatever, and so the problem that Eva's pointed out is that the transmission constraints may mean that there's a very limited amount of competition there. So there may be market abuse then. So that looks to me a rather tricky problem. Just quite how you organise a market where there's something energy which looks like it's suitable for contract design, but where the transmission constraints are going to cause there to be lots of fragmented markets.
In fact, you foreclose the market, and so you prevent competition through those long-term contracts. That's the argument. So, in fact, you should not have those long-term contracts with a dominant incumbent because you prevent entry into the market.
Entry, yes. Oh, I see. If it's already, yes, the transmission constraints are there. There's only a dominant provider.
Yes. But it can be fixed, don't you agree? That, I mean, it's not going to be, there'll be some loss, but they're not long term. They're limited length, and you artificially introduce competition somehow. Don't you think there are ad hoc fixes that would work well enough? I mean, that's what's done today. In Alcoa, it's not. I mean, there's a lot of restrictions on these contracts. They're not just a pure bidding process. And it works, and it's working today. It's not perfect. There aren't more than 5 actors. There's only a few actors. Yet.
Well, there is such a contract in France between EDF and the large industrial consumers, but it took, I guess, 2 years to get the contract through competition authorities in France.
That's because there's only one EDF.
Well, but that's true. But on the other hand, if you have a fragmented market in terms of generators, then you are not sure about. Well, they may not provide the adequate guarantee for signing those contracts. The utilities are not doing very well these days, so you prefer to have a big guy as an industrial consumer, I mean, as a counterpart.
But you can have a reasonable number of generating companies that are dispersed very widely geographically, so that in any one area there's still quite a few of them, but they're still very large.
Well, okay.
And to come back to Frank's point, or Eve's point, there are a whole variety of contracts that are out there. One of them is that a large company issues equity, and people hold that as a form of long-term contract in the risks that the company faces. And the particular risks that are most problematic are the ones where the uncertainty in what you're selling is very high, and ancillary services where technology may change, and capacity markets where the tightness of the margin makes a massive difference to the value of the output and how many hours you run, are particularly risky. But if you're running a baseload or even a mid-merit gas plant where you're buying gas and you're selling electricity based on the price of gas, the amount of risk you bear is modest, and it's passed on through the equity to the shareholders. So that hasn't proved to be a particular problem.
Well, I think the comparison with the gas plants these days is not. It's a little bit embarrassing, though. If you had signed such a contract 5 years ago, you would feel very bad.
Oh, right.
That's what equity markets do to you.
Yeah, but that may be also a reason why people would not be interested in buying equities in the utilities these days,
As opposed to banks.
But it's not sufficient to say that that's what equity markets do to you, if the consequence of that is that National Grid can't balance the system because the gas isn't there to balance the wind and the lights go out. You can't just say it's equity markets.
Yeah, but what's happened there is the company's still going to run, because there's the difference between the electricity and the gas price that incentivizes it to run. It's just that the
We've had an awful lot of gas plants mothballed.
Yeah, but the investment cost the big risk was the investment cost, the upfront investment cost, and that's where the equity shareholders taking that risk. So that does seem to work there, doesn't it? That you've displaced that big.
Okay, today, would a large industrial consumer be willing to make a contract with a utility for something based on gas, or on coal, or on nuclear, except if there is a feed-in tariff that guarantees the price of the nuclear?
There's no sunk cost, you see. I mean, Alcoa's already done it, and so it's easy to design a contract that's
But the contract is there to pay for the sunk cost. That's the whole of the contract.
You
In fact,
mentioned
it's to
Alcoa.
guarantee that the company will invest in that type of plan.
I think you misunderstood.
And the contract will contain something for the capital cost and an indexation on the fuel cost.
No, you misunderstood. I said there's no sunk cost. It's very easy to define, I believe, okay? It would be easy to set up contingent contracts with Alcoa because it's very easy for them to sign on. They don't have a sunk cost. And so saying that their payments will be contingent on
Alcoa, yes, but the generator.
But that's why generators are much more difficult. Absolutely. But there's such a huge amount of ancillary service.
And David, you made an assumption if you have plans that are sufficiently diversified, provided the network will allow for those contracts. So that means that the transmission company has to say, okay, we will deliver, and we will not be able to interrupt the contract 2 days in advance. In fact, when you have the contract these
Those
days,
are in the terms of the contract. You can
well,
have
but
firm
except
or
that the
interrupt.
transmission, the TSO like to be able to want to keep the possibility of interrupting the transmission.
National Grid gives you firm contracts for access onshore.
If we could shift,
But
I
across
think
borders,
Depends on the borders.
yeah, okay, it ends on the border.
the discussion is going too much into economic details, so we're losing a little bit part of the audience. This is mathematics, I think. It's all should be about mathematics. So if I could shift discussion into interesting problem of control, which is expertise of many people here. So everything what Sean said, it's predicated on, and what Frank said, is predicated on distributed, decentralized control. In the traditional way, idle way of controlling the system, is solving large optimization problem, Lagrange multipliers. So that's what National Grid and utilities do. And then broadcast those values of Lagrange multipliers. But that assumes centralized solution, it's bid, subject to market power, and etc. and etc. So the question is, could we do it? Could we calculate, could individual market players calculate their own Lagrangian multipliers in a decentralized way? And this is something what we've been discussing a lot with Frank about. So the question is, can we run the whole show in a decentralized way, having some proxies for Lagrangian multipliers in a power network where everything is tightly connected, and traditional conventional wisdom is you can't do it. You need National Grid or whoever to tell you to calculate the whole thing and calculate what the Lagrangian multipliers are. So open discussion.
Well, I have another question which is simple. Can we run the whole optimization given all the actions that will take place, well, from upstream of transmission to the demand response? Do we have some conceptual model where we can keep the control of all those activities with fixed transmission and distribution capacities, to simplify?
So that relates to question you were asking to Andrew. Basically, can we get rid of National Grid? Basically, can we? Can we run the whole thing?
National Grid would solve that. National Grid would solve that. Is National Grid prepared? Does National Grid think that it can do that? Or as a matter of fact, are people, do they think they can do it?
Chris?
Well, I think there's a question of where we need to switch to. There are the two questions of where we can go to distributed control and where we need to. And it seems clear to me anyway, that in future distribution networks, if we have a very large number of customers who are active participants in the operation of the network in some sense, then there has to be some substantial measure of distributed control, because the centralized optimization problem that you can write down in principle but becomes computationally intractable in practice. However, at transmission level, it's less clear. It's not clear to me at all that one needs to switch to distributed control, provided that you can aggregate everything within the distribution networks to a sort of virtual generator at the grid supply point, and whether you and that seems so. It seems to me that we we probably can continue to run a transmission network in something not so dissimilar from the current way. Then you get into the questions of, well, can you do it? Can you distributed control in a transmission network while maintaining operational security to current levels? And also, then you get into the sort of next question: if you can do both, which is the better idea? But there's also the important point that I suppose at transmission level, once you go on to very large systems, we actually de facto do have distributed control across the European system, because we have national system operators and fairly somewhat, I think maybe somewhat ad hoc ways of setting up the rules for trades between them, which are not directly grounded in the fundamentals of power system, the physics of power systems.
Andrew, well, you are a control man, National Grid, so you keep the fingers on the handles.
I'd just like to put this out there, that in the old days, your model of the system was that you have generators connected to a transmission network. The transmission network ships the power out, and then you have distribution networks, and they just have to worry about what goes on in their particular area. And if you have as something like National Grid doing an optimization problem, they can do an optimization problem at one stage, and then that can be the sort of environment that the distribution network does at its stage. And if everybody does their job properly, it seems to me reasonable to assume you get to a unique optimal solution. If you've got a network, as we are moving towards now, where the distribution networks have lots of embedded generation that can pump power back in, it's no longer as simple a solution, and it seems to me quite likely that there is more than one optimal or nearly optimal solution. And if one distributed operator comes to one conclusion about that, what that solution is going to be, and another one is going for a different solution, those two problems you end up with something vastly suboptimal. That's my concern.
What do you mean by that? Actually, that's something I'd like to understand, because so in the New England ISO, the optimization problem to get the exact optimal value is intractable. They can never do it. But there's a whole range of solutions that are within 1% of optimal. You know? And the reason they have to get the exact optimizer is because of lawsuits by the coal generators if they don't, if they get some ad hoc fix. So, I mean, is it really that sensitive? I mean, is it really that important? In the U.S., it's not. I mean, getting two coal generators there or two coal generators there in the day-ahead market, most of the time it doesn't matter.
It depends on the constraints.
Yeah.
The constraints can be absolutely critical.
But wouldn't that, I mean, you say there's a lack of uniqueness though. I mean, so you have two solutions, with constraints you have two solutions, and one is very expensive and one is very cheap. That's what I was wondering. Why is that?
Imagine you've got two distribution networks, both of which have got the capacity to export power, and there's a link between them which can get overloaded.
Yeah.
If both of them are producing, you can imagine a situation in which some link suddenly receives much more from the optimal solution. Doesn't matter which one of them is doing it, producing either A or B. And A says our optimal solution is for us to do it.
Oh, you mean local optimization?
Yeah.
Oh, I'm sorry.
So when they do their local optimization, you get things which conflict.
The New England ISO, I misunderstood your point. So the thing is, I think we should have air traffic controllers in the flight industry. We should have something similar. We do need that central air traffic controller to take those global information into account. And so a hierarchical structure like we have today makes sense, because of course we need that global information. It's just that it might be just a slightly more refined hierarchical structure.
That's my question to you. So do you really need this flight controller? Can Lagrangian multipliers, because that's the answer to the question, can be calculated in a decentralized way?
And my gut feeling is that I prefer to have the air traffic controller. I just know the delays and message passing, and I prefer. It scares me.
So Andrew, your job is secure, basically. We still need a traffic controller. Yeah, Frank.
So I think if one could foresee the future, one would expect the answer to these questions to be some mix of things. The air traffic controller, the transmission grid's not huge, really, as a graph. But nonetheless, it's kind of interesting to just do the thought mechanism. What is it that locally could be known? Because one thing we can predict about technology is that anything concerned with information processing computation that can be done will be able to be done at almost zero cost. So interesting question is, what is it that in 10, 20, 30 years' time, is it that the fridge will know?
Yeah.
The fridge will know lots. So it'll know the frequency.
Yeah.
It knows that now. It can know that now. One of your diagrams, so two of your diagrams provoked this thought. One of them was the diagram that told me the phase throughout that whole thing. Now, could the fridge conceivably know the phase?
Yeah.
And then the other diagram that provoked thought was that most mornings, if I understood you correctly, most mornings in some region or other, when you're eating your breakfast, there's minus 100. There's negative prices somewhere or other.
Minnesota, all the time. The wind blows, the price is negative.
It just kind of looks like when the fridge, the fridge just ought to turn on then.
The reason I get scared is that nobody has solved decentralized control. Nobody decentralized control. Even if I knew even if I had infinite computational power at every node in the grid, I don't know anything about decentralized control. Robust control solutions. There's no, but a hierarchical solution. I have techniques to imagine how it would solve.
Yeah, but that could be because by control you're thinking of the aircraft. You're trying to control it very, very well. Whereas the fridge turning off when the price is minus 100 is a crude response, which is not it's not fine-grained control, but it's nonetheless useful to the system. So it seems to be an interesting thought process. What is it that just logically in the future is what does the physics tell you? Now, I'm not requiring a smart grid or a communication network, because that will have delays. It'll have robustness problems about software. It'll have all sorts of points of failure to have a communication network. So when I'm saying that, what does the fridge know? I just mean the fridge is not relying on anything other than it's connected to the power system. It just monitors it can monitor the frequency now. It could perhaps know the phase. What else? What is it that it could know?
I challenge that. So the thing is that two-way communication to every pool pump and HVAC to the grid would be absurd. But for every pool pump and air conditioning unit to receive the regulation signal, and that's the work with on our blue ships. The pool knows the regulation signal and maybe knows the local frequency measurements. That's not expensive, is it? I mean,
No, I'm sure the answer will be some mixture of all of these things.
A little bit of global information.
I just find that extreme challenge of just as a straw man. It's an extreme challenge. What is it that it's not conceivable for the fridge to know? And what is it that we can reasonably expect?
And it could be beautiful waterbed effects. It could look like a gigantic waterbed. It's too much local information. You could get fantastic oscillations across the UK.
How would you know that your solution is optimal? Because the problem is non-convex, so you may have local solutions.
Undoubtedly, and that's why you're going to need the air traffic controller at some level, because what you're going to do is you're going to have to solve that the non-local optimum in some centralized way. But nonetheless, it could well. That doesn't mean you're not also going to be having individual electrical items that just have a sympathetic response to the grid. This is absolutely the way that, Jean-Yves would know lots about this, but that's absolutely the sort of philosophy behind a lot of the internet engineering, that the applications which are run on your PC and run between your PC and the server are crudely sympathetic to the level of congestion. It's a requirement of them that when congestion goes up, it's kind of like a real-time interruptible supply contract. is kind of like the condition upon it being connected, being allowed, being standard compliant, is that it has a sort of smooth, interruptible supply contract.
But I think you'd need communication links in terms of the grid, because apart from frequency, if you look at the angle signal or power balance signal, whatever, you'd need some reference, some communication. Yeah. Sorry, before, just to widen the discussion to other people.
Yes, well, it was to react perhaps also to, it's very attractive to have appliances react to frequency. But I was wondering whether it's a good design idea, because the frequency is really global. I mean, a generator trips in France, the frequency changes in Eastern Germany. So all the fridges in Eastern Germany would change because the line was broken through a storm in South, East, and Western. So we're really making the system completely global. So I'm not sure we understand what it would mean and whether it would really work.
That's the
As
water
opposed to
bill.
that, one could imagine having market aggregators, demand response aggregators that could send a signal on a network bus, signal injected at the medium voltage transformer. It would be a broadcast signal that has the same effect. That would be much more, perhaps more complicated, but as you said, the cost of communication and computing goes away in 30 years. So we would have more control of it. It would be one actor, like a demand response actor that we can stop, or would not be so finely, intimately buried in the system as frequency is. I would be unsure whether we're not taking risk.
You need to think about it. It's absolutely the case. Over the synchronous island, the frequency is the same, so that response to the fridge is valuable if there's a sudden trip out in it, and your first reaction is everything, all everywhere, should try and reduce their demand by 1%. And then you get that because 1% of the fridges do it. It's not if you've got a transmission constraint in between, but that often is your first. The reason that the net present value calculations for the fridges was so good is because that is what happens. You do have transmission constraints and various things which will cause you to want to do other things as well, but reducing the load is a help usually. But the philosophy is interesting. The philosophy, because it is the case that the computing and the communication will get cheaper and cheaper and cheaper. But the philosophical thing about measuring just locally is that the communications, while it's cheap to do, it has a point of failure that is, a software bug in the way you've set that up could make a big difference. And it's so that's why I kind of find provocative the straw man of saying, what is it that just the physics, if I'm connected to the power system, I'm getting a power signal through this alternating current, what is it that simply because of that I know? And I know incontrovertibly in the sense that it's not a mistaken information signal. I'm actually measuring it. I think it's useful to think of that, even if that's only a small part of the whole solution.
But again, the difference compared to the TCP signal is that I am in Eastern Germany, my fridge gets a signal because there's a local problem somewhere in the southwest of France. So the signal is global, whereas on TCP you get a signal if there is a problem on the path that you're using.
Right.
Here everything is interconnecting and
Right,
taxing everything.
But suppose something happens in the south of France, you'll only notice a frequency change in East Germany if the thing that's happened in the south of France is so large that the frequency across the whole synchronous island has changed.
Well,
The frequency is the same on the.
So this thing in the south of France has been pretty big.
You don't need very large incidents. As you said, the frequency is really global in Europe.
And the first response of all the fridges in whole Europe would be to help it. It's just in the space of the next minute. It's about secondary frequency control when you need the different things. I'll be talking about it in my presentation later on. There was someone wanted to say, yeah?
Yeah, I was just thinking that there's another thing that worries me about having these crude responses from many individual actors in the grid, which is that at one point there would be a frequency signal and all the fridges see it at the same time. They see, oh, there's something to respond to here, I switch off. And suddenly you get a huge synchronization about vast in vast areas where they're all responding at the same time and actually causing you more trouble than they're helping.
Yeah,
And so somehow we still need something like the flight or the air traffic controller.
I'm sure you need a flight controller, but actually the people that worked on dynamic demand did look through that, and because the hysteresis loop in the fridge is two-dimensional, it's the temperature of the fridge and the frequency, that phenomenon turns out they sort of modelled this quite extensively, and that phenomenon isn't a big problem, because essentially the frequency change causes some of the fridges to go off, but because each fridge has got its own temperature, they all share the frequency, but they don't share the internal temperature.
But if it started to happen sufficiently often, you can imagine a situation where they all managed to get closer and closer and closer into synchronization.
Well, one could
So
imagine
you might need some form of.
Yeah.
I mean, but it's just solving the same problem we have.
But that's a problem. But these are problems. These are problems which you do need to treat. But these are problems that can be treated. And
But we're
you
relying
need-
on probability.
Oh yeah, but we rely on that all the time, everywhere.
It's not probability. It's not like probability like from nature. It's probability that's injected. I mean, some of the proposed solutions are to, if there's a regulation signal, you turn off the device with some probability proportional to the size of the regulation signal. That's a random number generated in a chip, and so it does have probability and a half or whatever. And so, and that's what's been done in telecommunications as well. You have randomization and some of the backup protocols. And those are very robust in telecommunications. So.
No, Chris?
Yeah, just to comment on, because there's been quite a bit of talk about optimality and whether you have multiple local solutions. Just to comment on the nature of, if you like, nature of optimality in these problems, based on an exchange that I had by email with Brian Stott, who wrote the code which underlies the optimal power flow engines in I think almost all energy management systems. And when you actually take the optimal power flow model structures which are embedded in transmission operators' energy management systems, they're really nasty optimization problems, and they include non-convexities in continuous constraints. You must have that just in any AC optimal power flow problem, because it's got non-linear equality constraints. You also have all kinds of integer constraints, disconnected feasible sets, everything you can think of. And so he was saying that in these practical problems, it really is a case of finding a good solution reasonably efficiently, which is operable in practice. And operable in practice might mean things like not taking too many control actions. I think one great difficulty we have in the academic community, it's very difficult to find out what these model structures which are used in practice actually are. I mean, most of the optimal power flow models one sees in the published literature are fairly idealized models. Also, another thing that it's difficult to find out is precisely what the relationship is between the kind of models that Brian was talking about that he's developed and models which are used to set LMPs, locational marginal prices, in American ISO markets. I genuinely don't know whether these are the same models, or whether the models used used in setting prices are slightly more idealized. And I think that this is something that we've. There's been various bits of talk for a while about among the IEEE Power and Energy Society about optimal power flow test systems, which hasn't really gone anywhere. But it's started to occur to me that it's a bit of a step back from having sort of test data sets. We actually need more visibility of what optimization problems people are solving.
So someone at the back wanted to say something, yeah?
Yes, just also maybe a pragmatic approach, considering the difficulty of controlling so many devices. I think taking the fridges as an example, it may be very hard to have a dynamic response of the fridges and prove that all these fridges with time delays and various things are going to do the correct thing altogether. And there may be most value in being predictable, right? So you could also imagine that you count on control schemes where you let appliances, basically be predictable first and foremost. So they give, for example, in response to a frequency event, they try to aim for a collective power, step response, a certain profile, which may not be dynamically functioning with frequency, but may have the value of being predictable, so that the controller in National Grid knows exactly what's going to happen next. Perhaps maybe not optimal, but it would be something that sort of would allow like a hierarchical system to work well. Right, so the central controller knows that
That's what I wanted
the
to point out
decentral
that-
operators
that's
are
why I
doing
pointed
a
out-
certain thing. These curves are going in the system, and they will behave like this for the coming 15 minutes. So we know how to adjust the generator.
Basically, the idea is, and I think the way the discussion is going, I have the feeling is that if Sean is right, basically, in terms of regulation, in terms of short-term control actions, we should forget about markets. Get some crude and proxy to market price, like your integral of the control actions, absolute value of integral, and just forget about markets. As long as it got roughly good thing, that's fine. Let's not worry about optimal price signals, because we can get into all kind of issues with market power domination and things like that. So basically, is the control engineer takes over rather than economists, right? While in the long-term market, kind of 15 minutes time scale, there's the energy price is important, and then the economist takes over. So there is this saying that give power to the control engineer, you'll get reliability. Give power to an economist, you get low prices. So there is the question in the shorter time scale is reliability is the key. So I don't know, Andrew, would you agree with that?
But that's Eve disagrees, so that's
Well, I'm not sure that you will get low prices. I guess you will lose a lot of coordination with the economists.
Or you will get rich
That will
economists.
So David, your economist point of view, would you be happy to give up control on the shorter time scale to make sure that the system is reliable?
But as I understood John, he was saying to do that, you need to know what can be supplied, and you don't know, so you have a market in order to elicit that, and you need to make sure that they actually do it, so you need incentives for paying them when they do it and penalizing them when they don't. Now, whether you call that a market or a contract or a control
So you need to take an
solution
economist.
is, as far as I'm concerned, essentially irrelevant. It's a solution to the problem, and you have to bear in mind, on the one hand, the contracting costs of doing things and the speed with which you want them done, and the faster you want it done and the more difficult it is to contract, the more likely you are to have devolved that power to a central agency, and then he signs contracts with people. And at the other extreme, you have traders doing it. And there's a pretty much continuum between them.
Mm-hmm.
Yeah, I think it's perhaps coming back to the sort of the theme that came up yesterday or on the first day, that simply that a lot of different disciplines are required, and one of the important things is that people everyone brings their own disciplinary expertise, but there are somehow within the team of people working on this, you do need the sort of a means of sort of aggregating the knowledge that everyone brings, and making sure that solution you come up with actually has accounted for everything that's important. So I think it would probably be the case that having an economist or control engineer working in isolation would be a disaster. But you need you just need both, and need to find the right way of using all of their knowledge.
Well, what worries me is that there are I understand some really big issues out there, like are the security standards and the design standards for the high tension transmission system, which were set out in the 1960s, still appropriate in a world with the ICT that we now have? Or could we save, what was the cost to the bootstraps, a couple of billion quid, by just running the current system more intelligently? And that seems to require a combination of a range of disciplines, but at the heart of it, somebody has to be saying, is it good value for money?
If so, you wanted to add something?
Yes, I would like to just change a little bit what I said about the economists. I think the real problems are the traders. In fact, but I think they're very good lobbyists, and they impose some simplification, and the European Commission in general tend to follow them because they push competition in a very particular sense. It's not a very short-term competition. And then they really drive the design. And that design is made for them to simplify their activity. And they push all the problem to the TSO. In fact, all the difficulties are pushed to the TSO, which have to, and we see that in the software that is designed for market coupling, where there are things in that software that are there just to make the system look like trading in for an ordinary commodity market, where the physical law of transmission have disappeared, where there are no ancillary services, and then that has to be recovered somewhere. And in fact, you have unnecessary complexity in those things that are due to the traders. Now, that is for the current system. Given what we heard in the first talk about the difficulties of managing wind, I guess this might become unsustainable in the future. And they are extremely powerful, and they are very well organized to write memos explaining that this thing is possible when we know that it's not possible. And the Commission, they don't justify that it's possible, they just state that certain things are possible. For instance, there was one where the meeting organized by David, where we said that we can do with physical right everything that can be done with financial right. That's just not true. And they don't justify it, they just say. So these are not economists, but they pretend to be.
David, would you defend the traders?
No, I mean, I think there is, Steve has put his finger on it, they're incredibly well organized. They do have some points. I mean, there is no question that the liberalization and integrating across wider areas has delivered huge benefits. I mean, just extending PGM west has delivered surprisingly large benefits.
That's PGM.
Yeah, and integrating across Europe and improving the use of the interconnectors between countries. The gains there are potentially of the order of billions.
They can afford to give 10% to Deutsche
doing
Bank.
it.
They can afford to give 10% to Deutsche Bank and Goldman Sachs.
Yes, the point is, we tend to think of the overall system cost and not worry so much, or politicians don't seem to worry enough about who gets the benefits that we realize by creating these improvements. And the experience in the markets I've looked at is, it isn't the consumers, it often isn't the generators, it's somebody else gets the money.
In PGM, it's Goldman Sachs and Deutsche Bank.
What's PGM?
It's Pennsylvania, New Jersey, Maryland originally, but now they're half of the U.S. And Goldman Sachs plays around with these financial transmission rights and sucks out billions of dollars. And Deutsche Bank was sending in false bids to try to manipulate the market, and was just fined last month $250 million, which might be just 1% of what they take. Who knows?
But would you say that traders are as well organized in the U.S.
Oh, I thought you were referring to the U.S. the whole time. I mean, it's an incredible scandal in the U.S.
Because once Nico Neil said we never listen to traders.
Oh no, the whole thing is that Deutsche Bank they've been kicked out, but Goldman Sachs is just in their basement.
They're using your financial transmission rights.
Well, the problem is that we don't know how to solve the guaranteed transmission. But the physical or financial.
But you know,
It's amazing.
I'm confused by how simple it is. All these problems come down to that. Yeah, system optimization is good. We want to make things work more efficiently, and there are lots of ways to do that. But individual traders and companies and so on aren't interested in that. They're interested in making as much money as possible, in optimizing their own interest, and that's quite different.
True of customers as well.
Yeah, but if you have the right market structures, then there'd be incentive to create the infrastructure so we could play our optimization games. I mean, that's the problem. There hasn't been in the U.S. at all the right market structure to create the resources we need. And so economics would be key to creating those resources, and then we could do the optimization because the optimization's not that hard. I mean, New England ISO, I could on MATLAB solve the optimization problem. They can't solve it because of the market.
Can you repeat?
So, the optimization problem faced by every hour at the New England ISO, we could do it on laptops in MATLAB. Okay, it's just a linear program. We'd run the simplex algorithm, and then we'd stop once we're in 1%. We'd be happy. But they can't get their algorithms to converge because they don't care about the value. They care about the optimizer. So the difference between this solution and this solution is a penny. But if they pick the wrong one, they get sued by the coal company. So they have to pretend that they got the optimizer, and that they can't do. And so the market creates incredible combination of problems. Well, in fact, anybody, any of us could run a MATLAB script to solve that unit commitment problem. It's not, that, I mean, well, actually, I'm sorry. The unit commitment problem, I need somebody who knows some good integer programming, but that's done. And then the continuous part is just an easy script to get within a quarter of a percent.
But they make their argument on the fact that they can solve the large integer
They can't,
programming.
but the integer programming, they can, but they can't solve the convex part, because they're trying to get the exact optimizer, and the problem's so insensitive that they run their algorithm for forever, it doesn't converge. And there's lawsuits there. So the biggest cost to them is lawsuits. And you know what I think the biggest solution would be? Is if they had a credit score, and they solved if they actually looked at the reliability as well, then there'd be a bigger differentiation between the producers. I mean, they don't have nearly enough information in their
They put so much emphasis on the progress in the software. This is difficult to believe given what you say.
Yeah, well, I've got these two papers with Wei Wang I mentioned to you. That was all based in New England ISO. My student, but they can't solve the convex part.
They can't?
Not the convex part. They're using all sorts of cutting plane methods, and they use some strange things because it's so huge. And it's the lawsuit issue. It's the fact that they're talking about, a penny difference, and nobody would care at all except for the lawsuits because they're on one.
Just because Vanna wanted to say something. Yeah.
I guess we are talking mainly about how to make things work, but we really would like to see the response from the customers. And I think we are forgetting the customers are human beings. And there are quite a lot of things that they need to see why they would participate. And I guess the absence of some of the social scientists here, I guess they will give us some other ideas for thought.
It's an important point we just made yesterday, that in the dream team we need the social scientists, because at the end of the day those fridges are used by people. And will they be happy that those fridges are grid friendly or not, because they want them to be friendly to themselves rather than to the grid. So social dimension, I think social science dimension is quite important. Social acceptance.
It is, for example, it is interesting to notice, that our EPS grant for the autonomic power systems. So we have the demand side participation, and it was kind of interesting to listen to some of their angle, and probably okay. I know that there are quite a lot of guys here, only a few women, but introduction of the two tariff systems actually brought far more work to women. That is what they did. That was a study in Sweden. They recognized that because there was a two tariff system, then women had to really reschedule their work, and it was actually a burden on them, not a help.
Yeah. 14 point. Well, depends how you divide your domestic duties.
That is okay.
Or if I do my washing, it will be more work for me.
Yes, but I mean, typically that was done by them, and it was not in a sense of gender thing. It was just really that it really brings some additional things to other people to do. So they should see also some benefits. From
We are nearing the end of the session, so any last points, please? New dimension, new reflections? No, I think everyone. No, okay.
I've just using your analogy of the air traffic controller and going back to my first talk. I mean, is this going to make a difference that our air traffic controller is going to be in the fog all the time because of the winds and the solar and the fact that these consumers are behaving differently? I mean, I don't know if it, a control engineer seems to say, if I have the adequate resource, I don't care. But I'm not really sure here.
No, it's not just that you need the resources, you need the right information architecture.
Yeah.
And so absolutely. And so basically, if the ISO, whatever it's called in the UK, in the United States, a balancing authority sends a regulation signal to 1 million pool pumps. They want to know that those pool pumps, on aggregate, follow that balancing signal. And so that you need that information architecture, and you need a control design that's robust to uncertainty and so forth. And so there's a layers of that you need. So I'm not saying with the right resources and the right information structure, I don't think the control problems are hard. That's my gut view.
But in view of the fact we have all these constraints plus potential frustrated demand, and we're just in the fog, are we making sure we're just taking the right path all the time?
I think that I think that's a control issue we can solve. I think that has to be solved. I think you can get reliable ancillary service from heating and ventilation and from Alcoa and flexible manufacturing. I'm sure that's a control problem we can solve. The problems that Johnny has mentioned, they're real problems, but they can be solved through control. The problem is getting those resources online.
And so being in the fog is just going to cost us a bit more?
Of course, we have to get, it costs money to get resources in place.
A final remark, perhaps, from David.
Here's a control problem that I think is difficult. Decentralize the optimal location, choice of technology, and transmission network.
That's not a control problem. That's a huge combinatorial optimization problem. Maybe I misunderstood you.
Or let me rephrase it, to do better than we do at the moment.
The thing is that just goes back to the point. So let me just, in the U.S., we put in incentives for cars without roads. We had incentives to put in wind farms, and we had no incentive at all to put in the infrastructure to support it. And so we should have had some way of having auctions for creating the resources necessary to mitigate that volatility. It was never done. And so you needed economists and engineers at the table at the beginning. And it's exactly lobbying that started it. General Electric wanted to sell wind farms, and they also knew they'd make money from the chaos they create. They knew that ancillary service was needed, and they know that they're making money now from the chaos they've created in the Pacific Northwest. And so if you had engineers and economists at the table before, we could have quickly gotten the ancillary service needs met. And we know that why? Because MISO, 1 year of putting in some sort of incentives for fast responsive generation, they got this huge improvement in the quantity of resources. There's an economic solution that worked, and but nobody even thought to talk about this. Nobody even thought to mention that we need an infrastructure to support the wind generation. It was just off the table. And now they're panicking. They don't have nobody, and it takes a while. It'll take a few years to get those ancillary services in place.
Okay, I think it's time to finish this session. I think it was quite fascinating, wide-ranging discussion, going perhaps a little bit at one point to economics, but I think for the interest of the audience, which is maths, I think those are very important questions in terms of control, how to design control mechanism, my control hat on. I think the control engineer is as important as economists to get everything right. So thank you very much for the discussion. We can continue. I don't think we have provided answers, but at least those very good questions. How to decentralize the whole thing, and what are the appropriate market structures. So thank you very much. There's lunch now, the usual way, in Churchill College.
The lunch is here.
Lunch is here, I'm sorry.